Yeah, good evening, everyone. Are you able to hear me? Am I audible?
Connection is little not good. It is coming. It is voice is getting cut.
Okay. Is this fine now? Still, the problem is there? Network issue?
No, it's good.
Okay, okay. So let's start. If there is any problem, if you are facing, please let me know. And okay, today we are going to the week 3. Week 3, we will not go through all the concept. So while going through the questions, we will revise the concept again and then we will do the problems. Okay, so before starting, let me introduce myself. I am Harsha from IIT Tirupati. I am a research scholar. So yeah, is the screen visible now?
Actually, full screen is not coming. It's very
Yeah,
small screen.
actually I don't know how to keep it in full screen. Let me just try here. Okay, I will try to write in big letters. If you are facing any problem in reading, let me know. Okay.
Yeah, last time it was properly shared. When you took the class last time, it was good.
Okay, is it very small? Like it seems
Small.
the same for me from
Yeah,
last
it is.
time. Oh,
It is small. This time it is small. Yeah, it's almost half the screen, like half of what you shared last time.
okay. For me, it seems to be the same. I don't know what's the reason.
Can you please stop sharing and share again once?
Yeah.
Like share the screen completely.
It's the same now also.
Yeah, it is the same small screen only. Okay, looks like that is the maximum screen we can get. Okay.
Uh, what about this notes if I am taking? Does this make any difference? Screen size?
No, the same size, screen size is the same. It is small only.
Is the problem is same for everyone or just one person? What about others? Okay, anyhow, let me start. I think I cannot solve it now.
I think, ma'am, you have logged 2 times. That's
Yeah,
why.
actually, I am sharing my screen through the iPad, and the video
Ah,
is on in
so
this
yeah,
laptop. Yeah, I'm using the
okay,
iPad
okay.
for writing. Now screen is also not visible, right? Sorry. What happened? Yeah, I will try to write in big letters. Other than that, I'm not seeing any other way now. Okay, let us start today. It's already late. So, in the last week, in the week 3, what all we have covered is the linearly span we have already seen. If S is a set A, what is span of S? That we have already seen. Okay, and what is a linearly independent set? What is a linearly independent set? And what is linearly dependent set? So I hope you have gone through the videos. Dependent set, and yeah, some way to find it, like if a set of vectors is given, some way to find this linearly extract a linearly independent set from that, or to extract a basis from that. So some algorithm for that. Okay, these are all the main thing that covered in the last week. So let us go to the questions mainly. So in between, if you have doubt in the concept, you can ask. So the first question is, so it is a very easy question. So I will give a set of vectors, and the question is to find whether it is linearly independent or dependent. Which of the following sets are linearly independent or dependent? So the first one is S1 equal to set of all 1, 2, 5, 1, 3, 1, 2, 5, 7, and 3, 1, 4. And S2 equals, okay. So are you able to read this? How is the size of the letter?
Yes, it is readable. Yeah,
Okay.
thank you.
Yeah, so can anyone answer what about the option A? Is this linearly dependent or independent?
Yeah, it is dependent
Yeah, the reason is,
because there are four vectors
yeah,
and it is a R3 space. So 4 will always be, if it is greater than 3, it will always be dependent.
Yeah, in R3, the maximum number of linearly independent elements, the number in that set can be 3. Okay, if one extra, like 3 element forms a basis. Okay, basis is a maximum linearly independent set. So, if one extra, any fourth element, if we are adding to a linearly independent or dependent, whatever, if 4 elements or greater than 3 elements are there in R3, it is always linearly dependent. Now, what about the second one? Maybe you can take 1 or 2 minutes to check whether it is. It is 3 elements, so we don't know whether it has. It is linearly independent or dependent. So you can just check for 2-3 minutes. Any idea? Or how we can check? Can anyone tell?
Yeah, we'll have to do the reduction,
Yeah,
matrix reduction, and see
matrix
rank
reduction.
of the.
So usually from a set of vectors, how we can extract a linearly independent set. So we will write it as a columns. All the vectors column wise we will write, and we will do the row echelon form, and corresponding to each pivot, that corresponding column forms a, like, it belongs to the linearly independent set. So let me write that. If we have 1 to 5 is a vector, okay, in this 1 to 5 is a vector, so we will write it as a column 1 to 5. Next is 2 5 1, 2 5 1, and the third one is 1 5 2, 1 5 2. Okay, so we will do the row echelon form of this matrix. So we will get 1 2 1. So I will do the calculation very quickly. 0 1 3, 0 minus 9 minus 3, and in the next stage 1 2 1, 0 1 3, 0 0 24, something like this we will get. So here it has rank 3. Okay, so corresponding to each column, see these three are clearly, we can see it is linearly independent. Okay, like this, if it is getting, we can say it has rank 3, we can say, and it is linearly independent also. That matrix has rank 3, so it is linearly independent also. So the vectors corresponding to these three columns, that is our original vectors, are actually linearly independent. Okay,
Ma'am, isn't it dependent because independent is only for trivial solution?
uh, independent is,
Only for trivial solution.
yes, correct. Independent is only for trivial solution.
So this is dependent, right?
See, here we can see the matrix is, our matrix is 1 2 5 1 2, this see the first matrix, our matrix. So this is the reduced form. Okay, so we, if we are finding, suppose this is our A and reduced form is A dash. If you are finding Ax equal to 0, the solution of this and solution of
Okay.
A bar x equal to 0, both are same, right? Okay, if it,
Everything is zero here.
yeah, if
Okay.
it has trivial solution only, what we will say, it is independent. Okay, so it has only trivial solution, right? What we have is, so the solution,
Yeah.
the equations corresponding to this is x1 plus, see, corresponding to this matrix, x1 plus 2x2 plus x3 equal to 0. Okay, and
Yeah.
x2 plus 3x3 equal to 0, and 24x3 equal to 0. Okay, if we are solving this, what we will get, x3 equal to 0 we will get from here. If we are substituting it
Yes,
here,
yes.
we will get x2 0 and x1 0. Okay, so only trivial solution is there. Okay, so it is linearly independent. The given set of vectors is linearly independent. Now, the third one is easy. What about the third one?
Dependent,
Yeah, reason?
because rank is smaller than n.
Yeah, rank is smaller than 3. Like if we are considering it as a matrix, there is a 0 row, there is 0 column. Okay, so that will not count to the rank. So maximum it can 2 only. So if it is 3, then only we can say independent. In general, if 0 is there in a set, that means 0 vector is there in a set, of course it is a linearly dependent. Okay, so that is the result we are using here. So third one, 0, the element 0, 0, 0 belongs to S3. That implies S3 is linearly dependent. Is that statement clear? Like what I said just now? That is, if 0 belongs to a set S, S is linearly dependent. Is this clear? Why this is true?
Is it because like when the number of equations is less, then we have to keep generating? So,
Can,
right?
can you repeat? Sorry, I didn't get you.
I'm saying when the number of equations is less than the number of variables, then
Yeah.
there are infinite solutions, and so they are dependent on each other.
Yeah, that is the correct. Okay, that's correct. Because in that case, what we will get infinitely many solution means other than 0. That is other than trivial. Like one non-zero solution will be there. So that is linearly dependent. That is fine. Otherwise, what is the by definition of linear dependence? What we will say if we are writing it as a linear combination summation a x equal to 0, at least one ai should be non-zero. Okay, that is the definition. The set xi is linearly dependent. Here, whatever the element in s1, what we can write, c into 0 plus uh, for example, what we can c into 0, 0 into x1 plus 0 into x2 plus etc plus 0 into xn. This is equal to 0. Okay, where S is over the set 0, x1, etc. xn. I am just using the definition here. Okay, what is S? S is some set containing some elements x1, etc. xn and 0. 0 is an element of S. So, we are taking S equal to 0, x1, etc. xn. Now, I am taking a linear combination of elements of S. Okay, such that here C is a scalar with C not equal to 0. Okay, non-zero scalar into 0 plus everything I am taking linear combination 0 into x1, 0 into x2, 0 into xn. Obviously this is 0, but there exists a non-zero element, okay, a non-zero scalar in this linear combination. So just using the by definition itself, we can say S is linearly dependent. Okay, whenever a set contains 0, it is linearly dependent. Clear? Now let's go to the next problem. Suppose U, V, W are linearly independent. Okay, show that u plus v, u minus v, u minus 2v plus w. Okay, our question is, if u, v, w are linearly independent, show that u plus v, u minus v, u minus 2v plus w is linearly independent. Okay, what is the definition of linearly independence? S set S equal to x1 etc. xn is linearly independent if what is the definition? If summation,
The
yeah,
linear combination, yeah,
in linear combination is 0,
gives AI is equal to 0.
yeah,
Uh,
for all I, a should be equal to 0. That is 0, the element 0 has one only one way of representation like this. That is write as a linear combination with all the coefficient as 0. Okay, so that is what saying by linearly independent. If we are taking a linear combination equal to 0, so all the coefficients should be equal to 0. Now just use this definition. Okay, can you prove the above statement? How we can prove?
and we'll take
Hmm.
A1U
Yeah, we will take
plus
the linear
A2U
combination a1 a1u plus
A2V
okay plus a3w.
plus A3 is equal to 0 vector.
Okay, since they are linearly independent, what we can say? A1 equal to A2 equal to A3 equal to 0, correct? That is fine.
Yeah.
But what we want to prove? U plus V, U minus V, U minus 2V plus W is linearly independent. For that, we should take the linear combination of the given three vectors and we should be able to prove that that coefficient are 0. Is that clear what I'm saying? We should
Yeah.
start from what we should
Yes.
get. Okay, we should get u plus v, u minus v, u minus v plus w is linearly independent. So we should start from the linear combination of those vectors. So let me erase this. So I'm taking the linear combination of a1 into u plus v plus a2 into u minus v plus a3 into u minus v, sorry, u minus 2v plus w equal to 0. Okay, now what we can do? Now we should go to the given condition. Given condition is u, v, w are linearly independent. So we should reduce this equation to in terms of some linear combination of u, v and w. So what is this giving? A1 plus a2 plus a3 u. Okay, I'm just taking all the terms of u together and a1 minus a2 minus 2a3 v plus w has only in the third term only we have w, that is a3 w equal to 0. Okay, from this equation what we can conclude?
Third element, we can straight away make it 0.
Yeah, we got
And
a3 equal to 0. What else we are having now?
yeah, so now a1 plus a2 is equal to 0,
Yeah,
and
a1
a1
plus.
minus a2 is equal to 0.
Hmm. Okay. Now let's write it in a systematic way. So what we are having is UVW is linearly independent. So the star is a linear combination of linear combination of this UV and W. Correct. So if we are having such a linear combination and UVW is linearly independent, we should have each of the coefficient equal to 0. So what we will get, a1 plus a2 plus a3 equal to 0, a1 minus a2 minus 2a3 equal to 0, the coefficient of u, coefficient of v, and the last coefficient of w, okay, equal to 0. From this equation, what we can say, if we are substituting the third equation to the other two, we will get a1 plus a2 equal to 0 and a1 minus a2 equal to 0. If we are just adding or subtracting these two equations, from this we will get, suppose if we are adding two equations, 2a1 equal to 0 and a1 equal to 0. If a1 equal to 0 and a1 plus a2 equal to 0, what does that means? A2 is also 0. Okay, so we got a1 equal to 0, a2 equal to 0 and a3 equal to 0. Correct? We started with a linear combination of given three vectors, a1 into u plus v, a2 into u minus v, this one, a3 into u minus 2v plus w, and we got all the coefficient equal to 0. So what does this means? The three vectors are linearly independent. So u plus v, u minus v, uh, u minus 2v plus w is linearly independent. Is that okay? Okay, I hope others also answer to my questions. Okay, let's go to the next problem. So I will give a set of vectors. Which of them forms a basis of R3? That is the question. So let us start with the first one, 1, 1, 1 and 1, 0, 1. Yeah. While I am writing the remaining questions, you can check with the first two options, like whether it is a basis or not. Okay, we have five options. Uh, Out of this, some two or three, you can very easily say whether they are basis or not. So, can anyone tell which one does not form a basis or which one forms a basis?
Ma'am, A and E will not, because they are two vectors and four vectors.
Yeah.
Now B, C, and D we have to see.
Okay. So the thing is, we are taking the
B
elements of
B
R3.
part there is zero vector
Yeah.
involved which
So
disturb linear independency. So B
B is
doesn't
also
form a
not.
basis for R3.
So only we need to uh, check C and D, correct? Okay, so basis, so
No,
let me,
even B also, if it is linearly independent, like the last question,
hmm.
then it will be a basis, right?
But will it be linearly independent B?
Like last question was linearly independent. It had 0, 0, 0.
No, no, if 0, 0, 0 is there, it will be dependent always.
Okay, okay,
Uh,
okay.
that is what I told. If 0, 0, 0 is there, we can take the coefficient of 0 as some non-constant, some 1 into 0, 0, 0, plus all other,
Yeah,
we can take 0 into something. Okay. So,
I got confused. Yeah, you're
yeah,
right. Thank
okay.
you.
So, what we can, first of all, basis means in R3, we already know it will have always three elements in a basis. Okay. So, if it is less than three elements or greater than three elements, either it will affect spanning or linearly independent. So, okay. Now, first option A, we told it is not a basis. So what is the reason it is not a basis? It has two elements, okay. But by the definition of basis, it should be linearly independent and spans. Does it spans?
No,
No. It is linearly independent only. You can check it. But it does not span R3. So uh, since it does not span R3. And we told about E. What is the problem with E? Does it spans R3? Yeah,
it
actually,
is
yeah,
linearly independent,
it is
dependent.
linearly dependent. Actually, it will span full R3. You can check that. It is linearly dependent. So that is why it is not a basis. And in the option B, what we have is 0, 0, 0 belongs to say B. Okay. So not linearly independent. So not a basis. Now we have only two options remaining. Okay. So first question is option C, 1, 1, 1, 1, 2, 3, 2 minus 1, 1. Okay, I think you can do it yourself. So what we can do is, we can check, there are three elements. Either we can check whether their spans are 3 or whether they are linearly independent. So whatever, what we will do, we can just write it as a matrix. So in this case, either you can write it as a column or row. It actually does not going to matter. If rank is equal to 3, suppose we are writing row wise, and row rank equal to 3, then column rank also will be equal to 3, correct? Because row rank and column rank are always equal. Okay. So either we can write it as a column or as a row. So let us write it as 1, 1, 1, 1, 2, 3, 2 minus 1, 1. Okay. So what I am doing is, I am writing it in a row wise. Each vector I am writing as a row. Okay. So let us do the, okay, I am not doing all the calculation. After some, what we will get is 1, 1, 1, 0, 1, 2, 0, 0, 5. Okay. So for option C, okay, you can do the in between calculation. You can do. Okay. So this is what we are getting, the echelon form, raw echelon form. So from this, what you can conclude?
Yeah, it is linearly independent.
It is linearly independent.
And spanning, how will we prove? I don't know. Like, can you please tell how we can prove spanning?
Yeah, actually, For spanning also we can prove. Before that, if we are getting three elements, linearly independent element. Okay. Now, can we say that is a basis of R3 or not? We don't know about anything about spanning.
Yeah.
Of course, because basis can have maximum three elements. Correct? Because we have three elements, this is linearly independent. Suppose I am adding one more element. Suppose it does not span. Okay. Suppose this 1, 1, 1, 1, 2, 3, 2 minus 1, 1 does not span R3. Then what we will get? There exists some element XYZ in R3, okay, which does not belongs to the span of this set. Okay, so what we can do? We can add one more set to this, one more element. 1, 1, 1, 1, 2, 3, 2 minus 1, 1, XYZ. Okay, such that the total one spans R3. Okay, but it leads to a contradiction. It leads to a contradiction. Why? Now it is not linearly independent. Okay, linearly independent we can have maximum 3 only. So one more adding means it is not linearly independent, correct? Or directly if I am saying, suppose any element x, y, z. Okay, I am writing it as the given elements are 1, 1, 1, 1, 2, 3, 2 minus 1, 1, 2 minus 1, 1. So C1 plus C2 plus C3. Okay, 1 minute. What we got is the matrix, we reduce the echelon form, and from this echelon form we got three elements. Okay, so we got it is linearly independent. Now the problem is whether it spans or not. So we can check whether it spans or not. So what we want to prove is, if we are taking any xyz, if we can write xyz as a linear combination of the given three elements, then we can say the 1, 1, 1, 1, 2, 3, 2 minus 1, 1, that set spans whole R3. Correct? Uh,
Yeah. Yes. Yes.
okay, if this is satisfied, then span of 1, 1, 1, 1, 2, 3, 2 minus 1, 1 will be equal to R3. Okay, we are taking some arbitrary element xyz from R3. Now, from this, what we will get? C1 plus C2 plus 2C3 equal to X. Okay, C1 plus 2C2 minus C3 equal to Y. C1 plus 3C2 plus C3 equal to Z. Again, if we are writing it as a matrix form, 1, 1, 2, 1, 2 minus 1, 1, 3, 1 into C1, C2, C3 equal to XYZ. Okay, now what is this matrix actually? It is just the matrix. See, these entries, these vectors, we have written it in a column wise. Okay, that is the basic idea why we are writing it as a column actually. Okay, so these vectors we have written it as a column. Earlier we have written it as a row. As I told, since row rank and the column rank are equal, like whatever writing it is okay, because we just need to check whether linearly, if there are three elements, we just need to check whether it is linearly independent or basis. In order to check, it is a basis of R3. Okay, here from this row echelon form we got rank of this matrix is 3, correct? rank is 3. So if I am taking the transpose also, it like whatever I am getting here, it is the transpose of the above matrix. Okay, so it has also what is the rank?
3.
3, because here if I am doing row echelon form, I will get to the row rank, correct?
Yes, yes.
Okay,
Hmm.
that row rank is the column rank of the old matrix, like because it is just taking a
Hmm.
transpose. Okay, since row rank and column rank are equal, it should also have rank 3. Okay, so rank 3 means it is invertible, right, this matrix?
Yeah.
Yeah, if it is invertible, can we find c1 c2 c3 uniquely?
Yes.
Yes, because see, this is our matrix A, X, B. This is A, this is X, this is B. So we got rank of A equal to 3, which is equal to rank of AB. See, whatever coming in the B position, like after some echelon form, whatever comes in the B position, since rank of A is 3, rank of AB is also 3. And this 3 is the number of columns. Okay, in this case we told we have a unique solution for the C1, C2, C3. Correct? That means what we are having is here C1, C2, C1, C2, C3 has some unique solution, some non-zero solution. Okay, will it be 0?
No.
No, if
Because
it,
XYZ are not 0,
yeah,
so
yeah, if XYZ does 0, it is 0. Otherwise, it is non-zero. Okay, that unique solution is non-zero, and we got any xyz can be written as some linear combination of 1 1 1 1 2 3 2 minus 1 1. So this set is spans also, correct? We got linearly independent and span, so it is a
okay.
basis.
Yeah.
Okay,
Okay.
okay, now one more is there, we'll go very quickly. So D is, okay, I will write it as a
Ma'am,
matrix. Yeah.
question. So say if we check for linear independence
Hmm.
of the, say, three vectors for in the R3 space or n vectors in
Hmm.
the Rn space,
Hmm.
and if they are linearly independent, can we assume that they span also?
Yeah, obviously.
Okay.
Okay, if there are n vectors which is linearly independent, then it
Mhm.
spans. So that is actually uh, the dimension of Rn cannot exceed n. Dimension of Rn is n.
Yeah.
Okay, so any three element set which is linearly independent, then it is spans also. On the other hand,
And
if a
then,
three
to prove if it is a basis, then we
uh, uh,
only need to prove it is linearly
yeah,
independent.
yeah,
That is
it is,
enough, right?
yeah, only one, it is enough. It is linearly independent.
Okay.
That is enough.
Okay.
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 So yeah,
Right.
in D option we have, okay, I'm just writing this 1 1 2 1 2 5. So I'm writing all the vectors in row wise 5 3 4. I'm not doing the calculations earlier. So whatever we are getting, it is you can check it 1 1 2 0 1 3 0 0 0. So what about this? Will these three vectors form a basis?
No.
No, obviously no, because there is some zero vector. In the row echelon form, there is some zero vector. So it has rank 2 only. Rank 2 means maximum. It can have dimension 2 only. Okay. But R3 means it should have, it is having 3 dimension. Okay. These three vectors, if we are generating, or if we are taking these three vectors and generating the space, spanning that space, we will get maximum dimension 2 only, because it has rank 2 only. Okay, so what we can say, it is not a basis. Okay, now the next question is, find a basis and dimension of the subspace W of R2. Okay, so first of all, W equal to set ABC such that A plus B plus C equal to 0. The second one is W1, W2. ABC such that A equal to B equal to C. Yeah. What is the dimension? Dimension definition?
Our dimension is 2 of the real space. So I am a little confused here. Like, why is there 3 elements in the vector ABC?
Okay, okay, sorry, it is R3. I'm sorry.
Okay.
Sorry.
So now we have to prove, like, if we have to find the basis
Hmm.
of W1
Basis
and
of
W2.
W1. Yeah. And number of elements in the basis is dimension, correct? Yeah. Can you think of the dimension, or like what can be the basis? How we can find?
In W1, we are talking about R3. So their maximum dimension is 3,
Yeah.
exactly 3, and one condition is imposed here. So in case of W1, dimension will be 2 because there is formula about the dimension. And according to this rule, dimension of W2 will be equal to 1 because there are two conditions. A is equal to B and another we can say B is equal to C, or either you can take A is equal to C.
Hmm.
So according to formula, dimension of W2 will be equal to 3 minus 2. That is dimension of the given vector space R3 minus imposed conditions, linearly independent conditions basically. So dimensions of W2 will be equal to 1.
Okay. So what basically she is saying is, how many variables are there? How many free variables are there? Depending on, we can say the dimension. So here actually two free variables are there, but here, okay, I think I'll explain it. So first of all, let us see what is W1. What is W1? It is given set of all ABC such that A plus B plus C equal to 0. Now I am writing the condition is A plus B plus C equal to 0. From this I can write A equal to minus B plus C. Okay. So instead of A I am writing minus B plus C, and B is here, C is here. Okay. So here A, B are real numbers. Sorry, B, C are real numbers. B comma C belongs to real numbers. So I have taken this condition to this vector. Instead of writing the condition separately, I have taken it inside the vector. Okay. So whatever the vector we are having W1, it should satisfy, it should be in this form. Okay. From this we cannot further reduce because we are only having one condition here. Using that one condition, we have taken the maximum possible simplest form. Okay, so from here what we can do, now we can take all the terms containing B together. So we can write it as minus B B 0 plus minus C 0 C such that B comma C in R. B, C are from real numbers. So we can write it as the vector containing only B, terms with B, and the vector containing only elements with C. So if we are taking that B outside, B into minus 1, 1, 0 plus C into minus 1, 0, 1 such that B, C in R. Okay, so what we are getting here is W1 we are writing it as a linear combination of minus 1 0 and minus 1 0 1. Okay, now we got W1 as a span of two elements. W1 is span of these two elements, and this is linearly independent also. Okay, this linearly independent we can check it like this: minus 1 1 0, just write it minus 1 0 1. Its reduced form is minus 1 1 0 minus 1 1. Okay, so it has 2. Okay, so these two vectors are linearly independent. At that same time it spans W1 also. So this is the way how we find the basis. So write the vector, impose the given condition inside that vector, something like this. Check number of free variables. Here we have two free variables. Like arbitrary, we can give the values to these variables B and C. Out of this, take the B outside. So whatever we are getting, minus 1 1 0 and minus 1 0 1. These two are actually forms the basis of our vector space. So basis of W1 equals minus 1 1 0 and minus 1 0 1. Here actually I have taken B and C as free variable. The other way you can take A, C as free variable and write B in terms of A and C. That is here A, B, C. I can write A and C as free variable. So how I will write B in terms of this A plus C? Correct? Because A plus B minus A minus B. So the sum of these three elements should be equal to 0. That is the only condition. So you can check A minus A minus C plus C. This is 0. Okay. So there is no point in writing, like you can write in any way. You can take any two as free variable and write the third one in the terms of these two variables and simplify to get the basis. Okay, fine. Any doubt here?
Ma'am, this is R3, so shouldn't there be like three vectors forming a basis?
Yeah, to a basis of R3 should have three vectors, but we are asking basis of W1. Okay,
Yeah.
W1
Mm.
means what is this? A plus B plus C equal to 0.
Mm-hmm.
See, for example, I am giving you one element 1 2 3. Does this belongs to W1? 1 plus 2 plus 3 equal to 6 not equal to 0. So it is not in W1. Correct? W1 is set of all ABC which satisfies the condition A plus B plus C equal to 0. Here
Yes.
1 2 3
So,
does not satisfy, so it belongs to W1.
yeah,
Okay, that means W1 is properly contained in R3, right? It is not R3. There is some element in R3 which is not in W1.
correct. Yes.
Okay,
Yeah.
so
Mm.
dimension of W1 should be strictly less than dimension of R3. Correct?
Okay. So you're saying if it is a subspace, then the dimension of the basis should be less than
Yeah, it will
and
be. Always it will be. If it is a proper if it will be strictly less than, dimension will be strictly less than. See, because we got this one, basis of W1 is these two, minus 1 1 0, minus 1 0 1, correct? And
Okay.
we know that this 1 2 3 is not in W1, so 1 2 3 cannot be generated by these two elements, correct?
Yeah.
So what does that means?
No, I understand that there is some elements in R3 which are not a part of W1.
Yeah.
My only question is like one is the way of proving linear independence little bit different here, and second, second part you clarified that if W1 is a subspace, then its dimension has to be smaller.
Hmm.
So, but that independence part is showing like when we reduced it, it was not coming as coefficients 0. So I am missing something there at rank 2 when we found.
Hmm. Okay.
So here,
Hmm.
here it is not like we are saying linearly independent here for minus 1 1 0 minus 1 0 1. If they are linearly independent, then it should be reducing to like coefficients, linear combination to be coefficient will be 0, right?
Yeah.
But it is not reducing to to that, correct? I mean,
Okay.
am I
Let
missing
us
something?
check that. You just leave about this whatever I have written in this matrix form. So our matrix is minus 1 1 0, minus 1 1 0, and what is the other element? Minus 1 0 1. Okay. Minus 1 0 1. So what you are saying is, if we are writing the linear combination equal to 0 0
Yeah,
0, whether C1 C2 are 0, then only we can say linearly independent. Okay, let
yeah,
us check that. So what we will get, minus C1 minus C2 equal to 0. Okay, next C1 equal to 0, C2 equal to 0. Okay,
okay,
I am just writing
yeah,
like equating both sides, correct?
okay.
So
Hmm.
C1 and C2 are 0 means it is linearly independent. And also
Yes,
from this we got, see, any element we have written as B into minus 1 0 1 and C into minus 1 0 1, minus 1 1 0, minus 1 0 1. So it is spans W1 and these two are linearly independent. Two condition of base is satisfied, correct?
yeah,
Yeah. So the W1 has basis with two elements. These two elements form a basis, correct? So it has dimension
yes.
2. Clear? Or if we are just visualizing it geometrically, what is a plus b plus c equal to 0? It is a plane. Okay. See, x plus y equal to some constant that actually represents a line, right? Two variables. So in the same way, a plus b plus c equal to 0 represents a plane. I, that means it is something like R2. Okay, some two coordinates are enough to determine the whole plane. Is that clear?
Yeah,
uh, yeah, a plane means what we know, just like a paper. So one two axes are enough to determine, like with the two elements we can generate all the plane. If we have a line with one element, if we are taking all the constant multiple, that is enough to generate whole line. If it is a plane, like just like in R2, two elements are enough to determine the whole space. W1 here, it is an equation of plane. A plus B plus C equal to 0 means a equation of plane. So, geometrically seeing, we can say for a plane, two element is enough. So, you can directly say also it has dimension 2, like that way. Or if you want to find the basis, do like this only. Take the equation into this ABC. That means write one coordinate in terms of other two, and uh, then simplify. Actually, whatever you are getting, see here in this stage, actually whatever you are getting, B into sum plus C into sum, definitely it will be linearly independent only. Only thing is we should be careful while doing the first step. Okay. Okay, better you write like this and check whether it is linearly independent. Okay, any doubt, any further doubt?
No, it's clear.
Okay, okay. Now what about W2? Okay, we can write in the same way. Okay, someone already answered it. W2 equal to set of all ABC such that A equal to B equal to C. So just like the earlier example, what should be the next step? The given condition I should take into the tuple ABC. How we can write the tuple then?
A,
Yeah, A.
or
We have only one variable is here, one free variable. With the A should be from the field, scalar field R. Okay. Now we can write it as A into 111, A in R. So now what? Which element spans W2? What is the, what should be here?
111.
Yeah, 111. And what about 111? Is it linearly independent? Yes, right. And only one non-zero element means it is linearly independent. It's linearly independent. Clear? So
Yeah.
it is a 111 forms a basis of W2 and W2 has dimension 1. Clear? Because only one element in basis, so it has dimension 1. So next question. Extend the following set to a basis of R3. Okay. Okay. Before going to this question, let me ask one question. So, a question true or false. Let U and V be two vectors. Any vector space. U and V are two vectors. Then UV is linearly dependent if and only if one is a scalar multiple of other. Okay, that means if I can write one of the element UV as a scalar multiple of, that is U equal to CV or V equal to CU. Okay, in that case the set UV is linearly dependent, and conversely if it is linearly dependent I can write it as a scalar multiple of one as a scalar multiple of other. So this is the statement. So is this true or false? Any guess?
Yes, it is true
Is,
because in case of scalar multiplication, we can write like U is equal to CV, and if I take CV on other side, I can write U minus CV equal to 0. So
hmm,
in this case, coefficient of U is non-zero. So
hmm,
if linear coefficient, linear combination, one coefficient is non-zero,
hmm.
then that set of vectors is linearly dependent. So it
Yeah.
is true.
So we one side it is one is a, suppose we are taking the condition one is a scalar multiple of other. One is a scalar multiple means Suppose u is a scalar multiple of v. So what we can write? Some u equal to some cv for some scalar c. Then we can write u minus cv equal to 0. Okay. From this we can say linearly dependent. What is linearly dependent? uv. The set uv is linearly dependent. Is the last step clear for everyone other than the one who answered? U minus cv equal to 0. From there, how I am concluding it is linearly dependent? Any other can answer?
Yeah, it is clear.
Yeah.
Because coefficients are not zero. So,
Coefficients are, we cannot say. Coefficient of u is 1, it is not 0. We don't know about c. Just leave about that. But at least 1 is non-zero. Correct? That is enough
okay.
for
But
linearly dependent.
when we say U is equal to CV,
Hmm.
isn't it that C belongs to R and C is not equal to 0?
See, the case u and v are equal and v both are equal to 0. In that case, u equal to 0, v equal to 0, c equal to 0, everything in R, right? And uv is linearly dependent also.
Okay.
Okay. So in general, if it is non-zero, obviously c is also non-zero only. Okay. So there can be some case also, but from this, definitely we can say coefficient of u is 1, non-zero. So it is linearly dependent. On the other hand, we have to prove the other way also. Okay. What we need is uv. Suppose uv is linearly dependent. Now we should prove that one is a scalar multiple of other. So it follows the same way. Since it is linearly dependent, we can write it as C1u plus C2v equal to 0. Okay. With either C1 not equal to 0 or C2 not equal to 0. That is, at least one should be non-zero. Okay. Suppose I am considering C1 not equal to 0. It can be C2 also, you can try the other way. Suppose C1 not equal to 0. Then what I can write? U equal to minus C2 by C1 into V. Why I am taking C1 not equal to 0? This divided by C1 is there. If it is 0, I cannot do that. Correct? Now, if C2 not equal to 0, what I will take? If C2 is not equal to 0, then I should take V equal to minus C1 by C2 into U. Okay. C2 non-zero, that is why I have C2 in the denominator. So you should specify case when C1 not equal to 0, C2 not equal to 0. Okay. So from this both case, what we are getting? One element is a scalar multiple of the other. Okay. So here we can say U is a scalar multiple of V. So the other way also we proved. Correct? Now let us go to the next question. Extend the following set to a basis of R3. So first one is 1 0 0 0 1 0 and B 1 2 3 4 5 6. Okay, before going to A and B, let me give another one. 1 2 0 2 4 0. And the question is, can I extend C to a basis of R3? That means extend means I can add some vectors, like some vectors to the given set, so that after adding whatever we are obtaining, that set is a basis. That is what I mean by extending. Okay. So my question is, can I extend C to a basis of R3? That means if I add some one or two elements, will it become a basis of R3?
So here you have the same thing what you just told, like
Yeah.
u and v are multiple, like first is second two times
Hmm.
of the first.
Yes.
So they are both dependent.
They are
So
linearly
then if they are
dependent.
both dependent,
Ah.
then we need two more. To extend, we need two more vectors.
We cannot extend actually, right? Extend means I should keep all the elements here and add more elements. Okay. But here
Okay.
already I have a
Mhm.
dependent set. It is not going to be linearly independent if I am adding elements, correct?
Yeah.
Okay. If I am adding 1,
So
2,
we
3,
if we
whatever, I
if
cannot
we
find a
keep
basis,
yeah.
correct?
Hmm.
So if we
Yeah.
need to extend, if the question is to extend, first condition we should check is whether it is linearly independent or not. Here we cannot add no because it is linearly dependent. Now, to check whether two elements are linearly dependent, uh, we have an if and only if condition. One is a scalar multiple of other. So using that, what can you say about A and B? Sorry, 1 minute. Okay, the screen is not moving. Okay. Yeah. Okay, now you can see the A and B. Is this linearly dependent or independent? Just by looking at it, you can say now. Check A whether it is linearly dependent or independent.
Ma'am, your voice is not coming.
Oh, sorry. Uh, Now, what about now? Am I audible?
No, still it is not really.
This is like completely not audible or just breaking?
Maybe you can drop and join again because it is look like it has gone bad.
Okay, sorry.
Can you drop and join again, please?
Yeah, if I leave the meeting, there can be chance you will also. In case if you are also getting out of the meeting, please rejoin after 1 minute. Okay.
Okay. Yeah.
Am I audible now?
Yes. Yes.
Okay, 1 minute. Let me share the screen now. What about screen? Screen is visible?
Yes.
Okay. So, okay, we were talking about the sets A and B. Is this A and B linearly dependent or independent?
Independent.
Yeah, both are.
Linearly dependent.
Sorry, can you repeat? First one is a independent, correct? Because if it is dependent, one should be the scalar multiple of other, that we proved already if we have two elements. Okay, here we have two elements, and 0 1 0 is not a scalar multiple of 1 0 0. Whatever the scalar I am multiplying with one element, I will not get the second element, correct? So it is linearly independent. And B also the same way, it is not a scalar multiple of the other one. One is not a scalar multiple of other. So it is linearly independent.
Actually, in C part, vectors are linearly dependent. Not in A and B, they are linearly independent.
So which space? Which vectors?
1 2 0 and 2 4 0.
Yeah, third, not about third I am saying. I am asking about A and B. See, third is linearly dependent. Okay. Am I audible now?
Yes, you are audible.
Okay, okay. Any doubt? Any other doubt? This is linearly independent. Independent. This is also linearly independent. But this is linearly dependent. These are three things we are having. Do you have any doubt in these three things? Okay, so we have this is linearly independent. So we need to extend this set to a basis. Okay, so let us consider A. Our A is 1 0 0 and 0 1 0. Can you guess any element so that I am adjoining that element to the given set A so that it forms a basis of R3? Can you guess any elements?
0, the
Zeros.
z axis.
Yeah, z axis 0 0 1. An element from z axis we can take. So A union 0 0 1 forms a basis of R3. So clearly it is linearly independent. Like if 0 0 1 is added, still it is a linearly independent, and it generates whole R3. Now my question is, if I add 1 1 0 union A, does it form a basis? A union 1 1 0. Any idea?
I think it will not,
It will
because
not.
we
Yeah.
still we don't have access.
Yeah, x-axis is not there, but what is actually this 1 1 0? It is the sum of 1 1 0 and 1 0 0 and 0 1 0. Okay, so this set is actually linearly dependent. Okay, this is linearly dependent. Also, we have not generated the elements of z-axis, so it is not a basis. Not a basis. Okay. Now, what about if I am adding A union 1 1 1?
This should be linearly independent.
Yeah, it is.
I'm just guessing. Yeah.
Yeah, okay. It is actually, it will form a linearly independent and it will span also. So you can just check both condition. Okay, you just check it. It is actually a basis only. Just from the, as you told, it is like just through the induction we can say it is a basis. But check and verify that it is linearly independent plus it spans R3. Okay. Now we have one more question. B 1, 2, 3, and 4, 5, 6. Okay, so this is a linearly independent set. Now what we want to prove is we should take, okay, how many elements should we add to this set so that it will be a basis of R3?
1.
Only one is needed because 3 elements will generate basis R3. Okay, so we need one more element such that it generates whole R3 or it is linearly independent. So what we can take is, I am taking some arbitrary element. Okay, now what I want, these 3 elements are linearly independent. Okay, I need to choose an xyz such that 1, 2, 3, 4, 5, 6 xyz. These 3 elements are linearly independent. Then I am done, correct? Is that okay?
Yes.
Yeah. So we need to find xyz such that it is the 3 elements forms linearly independent. So in order to have linearly independent, what we need, this matrix, whatever I have written here, this matrix should have rank
3.
3. So we will reduce to the row echelon form and we will see what condition we can give to x, y and z so that it is linearly independent. So let me just write, this is 1, 2, 3. I am reducing for minus 4, 5 minus 3, right, okay, minus 6 and so what I am doing is R2 changing to R2 minus 4 R1. And what operation I should give here? R3 minus x R1. Okay, x times R1. So x minus x0, y minus 2x and z minus 3x. Now suppose this is 1, 2, 3, 0, 1, 2. I am just doing R2 to, just for the simplicity, R2 by minus 3. And here I will get 0, y minus 2x, z minus 3x. Now I need to uh, eliminate the y minus 2x. That is, I need to change y minus 2x to 0. So it will be 1, 2, 3, 0, 1, 2. And R3, we are changing to R3 minus y minus 2x times R2. Okay, 0, 0. So what we will get here? Okay, let me write it here. Z minus 3x minus y minus 2x times R2 is 2. Okay. So z minus 3x minus y plus 4x, z minus y plus x. Okay, so this is the element here, z minus y plus x. Okay, okay, this is nothing, I have just done the calculation here. When I am changing this to 0, the corresponding calculation I am doing here. So I am getting z minus y plus x equal to. Now, what if z minus y plus x equal to 0?
I think that is 2y
Oh, sorry.
on the top
Yeah,
equation.
correct. Sorry. 2. This is 2y, 2y, 2y. Z z minus 2y plus x. Okay. Okay. So what if z minus 2y plus x equal to 0? So this is our matrix. If it is 0, then
Z minus 2y plus x is equal to 0.
suppose
Then
this element I am taking. Okay. Then z minus 2y plus x equal to 0, correct? Okay. Now, if I am adding 1, 1, 1 union our set to 1, 2, 3, 4, 5, 6. This was our set. I wanted to extend it to basis. So, with this set, I have added one more element. Now, will it be a basis? Will it be a basis? No, right? Suppose if it is a basis, what we will do? We will write it in the matrix form. So that is what we have written here. 1, 2, 3, 4, 5, 6. Instead of x, y, z, I have 1, 1, 1. So after doing all these calculations, finally I will reach here. Here I will get 0. Okay. So it has rank 2 only at that time. Okay. Rank 2 means these 3 elements cannot generate whole R3. Or the third element 1, 1, 1 is a scalar multiple of, linear combination of other two. For example, I can say 1, 1, 1 equal to uh, 4, 5, 6 minus 1, 1, 1 by 3. Correct? Sorry. 1, 2, 3. See, what I am writing is this 1, 1, 1. I am writing as the linear combination of other two elements. So it is not a linearly independent set, right? So it is not a basis. So if this condition z minus 2y plus x equal to 0, we are getting a 0 row in the third row. Okay, that means the whole 3 element is not enough to generate the space. So we should not have this condition. It is equal to 0 should not be there. So what we need? We need z minus 2y plus x not equal to 0. Then only we will get a 3 non-zero rows. If it is 3 non-zero rows, then only we can have a 3 linearly independent set which generates R3. Is that okay? Any doubt? For example, I am taking 1, 2, 1. So here z minus 2y plus x is non-zero. Z is 1 minus 2y plus x not equal to 0. So then 1, 2, 3, 4, 5, 6 union the new element 1, 2, 1 forms a basis. Correct? Any doubt in this? Okay, if you have doubt, you can ask. We can clarify it and go.
so when this 1 to 1 which you found,
Hmm.
this is just by inspection we have to find, right? We have to put some values.
Yeah, we should find some xyz such that it is non-zero. You can take any other element. I am just giving one element, that's all.
Okay. So if we find any one element which satisfies this not equal to 0,
Hmm.
then
Then we can
it
add
will
that to the
be
original set. Then it will form a basis.
okay.
If any xyz which does not satisfy, that is such that z minus 2y plus x non-zero, what we will get? the original matrix, the reduced matrix, we will get 3 non-zero rows, correct? That does not matter what element it is. If it is x, if it is non-zero, that only it matters. If it is non-zero, we will get 3 non-zero rows, and we can say it has rank 3. So the space is linearly independent. The 3 elements is linearly independent. So it forms a basis. Okay, what element does not matter. Just take x, y, z such that z minus 2y plus x non-zero. That's all. Okay.
Yeah, you're saying because so that rank doesn't become less than n, right? Because rank has to be same.
Yeah, rank has to be 3 only because we need a basis of R3.
Yeah. Okay, fine.
So if it becomes 2, we will get a proper subspace. Correct?
Yeah, that will be dependent, like infinite solutions.
Yeah, infinite solutions will be there at that time.
Okay. Okay.
Now, in the same way, if we are having a set, extract a basis of R3 from the following set. So what we did is we got some set, we extended it to a basis. Now I will give one set, means obviously that set will be having more than 3 elements. From that I will take 3 elements so that it forms a basis. How we can extract such a basis from a given collection? So that is the next question. So first one is 110 011 101 111. Okay, this is the first question. How can we do this?
Hello?
Yeah.
Okay. Your voice was not coming, so I thought it has got disconnected.
Oh, no. Now, okay, coming or not?
Yeah, now it's coming.
Yeah, I think there is some internet fluctuation today. Okay, so yeah, what we were saying is I have one set, from this choose a subset of this set such that it forms a basis. Take a okay, here we have 4 elements, right? Is this a basis?
No.
No. So how can we take some 3 elements so that it is a basis of R3? That is the question. What are all that 3 elements? For that, the basic method is, we have already seen an algorithm to take the linearly independent elements out of the given elements. For that, if we have some v1 etc., some vk, okay, suppose this is some vectors. Now we will write it as column wise v1, v2 etc., vk. So this is one column. Okay, suppose v1 equal to 1 0 0. Okay, now here column wise means I will write like this all the elements. Okay.
Hello, ma'am, you're not audible.
Oops. I'm very sorry. Some internet issues are there. I can't do anything. Now, am I audible?
Yeah, now.
Yeah, please let
audible.
me know
Yeah.
whatever not audible. I will repeat again. Some internet issues are there. As of now, I can't do anything for that. Okay, so what I was telling is, from a given set, to extract a linearly independent set, what we will do is, we will write it as column wise. Okay, if v1 equal to 1 0 0, we will write it like this. So, like wise we will write V1, V2, etc. Vk. Then we will do the row echelon form. Okay. In row echelon form, whatever the non-zero pivot, that corresponding column we will take, and that column is a linearly independent set. So let me do it for this example. Here we have 1 1 0, 0 1 1, 1 0 1, 1 1 1. Okay. So these four are my vectors. I have written it in the column wise. Okay. Now what we will do is we will do the row echelon form. So 1 0 1 1 1 0 minus 1 1 minus 1, and again next stage. Okay. So we have written the row echelon form here. So what are all the pivots here?
The A11
Yeah.
and the A22
And A33. Okay.
okay.
So these three are the pivot elements. So the column corresponding to the pivots 1, 2, 3. These three columns. Okay. So these three column means we can take the corresponding column here. Okay. So this is a linearly independent set. That means column corresponding to the pivots. Three are linearly independent, and whatever remaining here, it depends on other columns, the other three columns. Okay. So we got a 3 element set which is linearly independent. Okay. So 1 1 0, 0 1 1, 1 0 1 is linearly independent. Okay, and we have three elements here, so obviously it is a basis. So what our set was, these three elements union 1 0 1 1 1 or something. Okay, this was our set. If we are removing this 1 1 1 also, this forms a linearly, this is linearly independent plus span. Okay, the three element is enough to form the basis. We can just pull out the 1 1 1 from the set. Okay, so that is how we are extracting a basis. Write it to column wise, do the row echelon form, and find the pivots and the corresponding columns. Okay, that vector forms the basis. Is that actually, suppose if we have two pivots only, okay, then it will not form. I have three pivots and the three elements which is linearly independent. That is why it is a basis. Okay, if I have two pivots only, I will get two elements. Obviously, two elements does not form a basis for the R3. So since I have three elements here, I am saying it forms a basis. Otherwise, I can say whatever I am getting, the columns corresponding to the pivots, whatever the columns I am getting, it is linearly independent. Since its number is 3, I am saying it forms a basis. Fine. Now the next question is, okay, this I think you can do it as a homework. It is the same kind of repeating. B is 1 2 3 3 4 5 5 6 7 7 8 8. Okay, so from this extract a basis. So this you can try as a exercise. just write each of the vectors as column, do the row echelon form, okay, and find in which row in which column the pivots are coming. Take like whatever the operation you have done, you know, like what are all the things you are doing, correct? So anyhow, whatever you are doing, it is just a row interchange only, that column interchange is not happening. So if pivots are in 1 2 3, go to the 1 2 3 columns of the first matrix, and that 1 2 3 will form a linearly independent set. Okay, for example, here actually 1 2 3 3 4 5 5 6 7 7 8 8. So after some, yeah, okay, after some operation, actually you will get 1 3 5 7 0 minus 2 minus 4 minus 6 0 0 0 minus 1. Okay, this is the thing we will get. So here the pivots are 1, and the next one is minus 2, and the next one is minus 1. So this corresponding to the first one, second column, and the fourth column. So we should take first, second and third, sorry fourth, then only it will form a basis. Okay, so just do the write the matrix like this, do the row echelon form, verify that it is the uh, row reduced echelon form. This one is the row reduced echelon form, and what are all the pivots, take the corresponding column in the original matrix. So that 3 forms the linearly independent set. Since there are 3 elements, it should span also. Okay, so it forms a basis of the vector space R3. Is that fine for everyone?
Ma'am, one question.
Yeah.
Uh, what is the significance of putting the vectors in the column form? Is it like how is it different from putting it in the row form, which we always do?
Uh, if you are doing row, you can put in row, but then you will have to do the column operation. That is the only thing. Okay, see, if we are putting it in the row form, we may be interchanging the row also.
Mm-hmm.
So if I have 1 2 4 here in the reduced form, that corresponding 1 2 3 in the original will not be the see, here I am taking 1 2 and 4. Okay, if I am doing uh, column operations, I might have changed this 3 and 4 already. So if the corresponding 4, if I am taking 4, it will not be the corresponding form, it can be 3. Okay, at some stage I have interchanged 3 and 4. Okay, so if you are taking in row form, you should do column operation. If you are doing in, if you are taking as column wise, then you should do row operation. That's all. You can take the other way also. Okay. Okay, then okay, next question is, let U and V be two subspaces of Rn. Which of the following are true?
Please explain again. Your voice is not audible in that question.
Yeah, ma'am, your voice is not coming.
Okay. Okay, I will just try to connect in another internet. You just let me know after that. Okay, give me 1 minute. Okay, let us check. How is it now? Am I audible now?
Yeah, yes, yes.
Yeah, let us try with this. Okay. So we have two subspaces U and V. So I'll give some statement. We need to.
If if
So
uh,
sorry.
if we take the previous if we take previous vectors in row form,
Huh.
yes, in this form, then what will be the procedure? Please explain that.
Uh, can you ask once again? I didn't get you.
If we put the given vectors in row form,
Hmm.
like first row, second row, third row, fourth row,
Hmm.
here in this question, you put like first vector 1, 2, 3, put in first column, second vector in second column,
Hmm.
and apply row echelon form.
Hmm.
In that echelon form, we apply only row operations basically. So, like if we put these vectors in row, like 1, 2, 3, put in first row, 3, 4, 5 in second row,
Hmm.
and last vector in fourth row. Then can we apply row operation, or we should apply column operations in that?
If we are putting in row, if our aim is to find the linearly independent vectors, we should find column operation. We should do column operation. For row, we should do column operation. For column, we should do row operation. Okay. But
Okay, okay.
if just if we are finding to rank only, we need to find the rank or something. You can put in any form, row or column, whatever you can do, and do the row echelon form. Nothing like if you are writing in column wise, row wise, whatever, it is okay because row rank and column rank are equal. So that does not matter. But our particular aim is to find the linearly independent vectors among the given vectors, write in column, then do row echelon form. Otherwise, write in row, do the column operation. That's the only difference. Okay. So okay,
Also,
oh, we have two spaces, subspaces of Rn, U and V. Now the first question is U union V is a subspace of Rn. Is it true or false?
it is false, ma'am.
Yeah, can you give example why it is false? If it is false, we need some counter example. Can you give two space U and V such that its union is not a subspace?
Yes, if we take R3 vector space,
Hmm.
and if I take U is x-axis and V is y-axis, like U is the collection of all vectors A, comma 0, comma 0,
Hmm.
and it forms y-axis like collection of all vectors 0, comma b, comma 0.
Hmm.
And if we add two vectors particular from u, uh, let us say 1, comma 0, comma 0,
Hmm.
and from b 0, comma 1, comma 0, and
Hmm.
the addition of these two vectors will be 1, comma 1, comma 0,
Hmm.
and that is neither on x-axis nor on y-axis. Actually, it lies between a plane,
Yeah.
between x-axis and y-axis.
Okay. So that is
So,
the thing. Sorry.
yes, in this example, we can say union may
Yeah.
not be a subspace, but if one vector space is contained in the another, in that condition, we can say union will make a subspace.
Yeah, that is correct. Let's not go to the further condition. One is contained in other and all. So let us just give me. Let us just see the example where the union is not a subspace. So what she was saying, u is the x-axis. Suppose I am just taking r2, whatever is fine, r3 also fine, and v is y-axis. So u union v will be the set of all x0 such that x in R union set of all y0 such that y in R. Sorry, 0y. Okay, so I am taking two elements 1 0 and 0 1 from U union V. Both belongs to U union V. But its sum 1 0 plus 0 1 equal to 1 1, which does not belongs to U union V, because it contains elements at such that 1 is always 0. One coordinate is always 0. So this does not belongs to U union V. So it is false. Okay. Now what about U intersection V? If U and V are subspaces.
Yes, U intersection we always make a subspace.
Yeah. U
We can
intersection.
prove it through regular usual way, like alpha x plus beta y. It will belong to U intersection V if we take x and y separately belongs to U intersection V.
Yeah. So we are taking X and Y in U intersection V. What we need to prove? Some Cx plus V also belongs to U intersection V. Okay. Before that, definitely 0 belongs to U intersection V. Correct? Because 0 belongs to U and 0 belongs to V. So it belongs to U intersection V. Now I am taking X, Y in U intersection V and a scalar R. Now, since it belongs to U intersection V, I can say X belongs to X and Y belongs to U and XY belongs to V. Okay, that implies since U is a subspace, Cx plus Y belongs to U and Cx plus Y belongs to V. Okay, so that implies Cx plus Y belongs to U intersection V. So U intersection V is a subspace. Now the question is, U plus V. U plus V I will define. It is U plus V such that U in U, V in V. That means I am taking all possible combinations. Like I am taking an element from U and from V, adding these two elements. So all such a collection I am taking as U plus V. Is this a subspace or not?
Yes, ma'am. Basically, it is linear sum, and
Yeah.
it always moves.
It is a linear sum. So we can prove, for example, we can say 0 belongs to U, 0 belongs to V. So 0 plus 0 equal to 0 belongs to U plus V. It is a non-empty set. And also we can consider two elements. Suppose x, y belongs to U plus V and C is a scalar. We need to prove that Cx plus y also belongs to U plus V. Okay, since x and y in U plus V, what we can say, x is some u1 plus v1 and y is some u2 plus v2, because u plus v is defined like that. Now what is cx plus y? C into u1 plus v1 plus u2 plus v2. Again, what is this cu1 plus u2 plus cv1 plus v2? It is again in the form. So this is an element of u and this is an element of v. Since u and v are vector spaces, so it should belongs to u plus v. Okay, so u plus v is also a vector space. Now question, u difference v. What about this? U difference v is not x minus y form, as what I am saying is set of all x such that mm, x in u, x not in v. Okay. That means I am removing all the elements v from u. Okay. Will it be a subspace?
Ma'am, but zero will lie in both.
What? 0?
Zero, that is identity element.
Yeah, it will not be
And
there in that.
according to given conditions, zero will
Yeah,
not lie in
u
U and
minus v,
V.
because 0 will be in
So,
v, 0 will be in u also. So that 0 is removed, like 0 is not in u minus v. So u minus v is not a vector space. For example, if I am taking the set S u equal to, sorry, v equal to 0, v equal to 0 and u equal to R2 itself. So u minus v means R2 minus 0. That means the 0 is removed from R2. Obviously not a vector space, correct? So that's all. So let me, okay. Okay, one more question we will do. U plus u equal to u. Okay. U is a vector space. The thing is u plus u equal to u. Can anyone, uh, is this correct or wrong first of all?
um, if we take U is identically equal to zero, then it is correct.
It is correct. So what we need to prove that both are same. Two sets are same. When we will say two sets are same, both u plus u should be contained in u and u is contained in u plus u. Okay. Now u is clearly u is contained in u plus u, correct? For example, what,
Yes, ma'am.
yeah, what we can say, u equal to set of all u plus 0 such that u in u. It is contained in set of all some u1 plus u2. This is this is the form of u plus v. Sorry, u plus u. u1 u2 in u. Okay. Now this is okay. U contained in u plus u. Now how we can prove u plus u is contained in u? For that, we will start with an element x in u plus u. We can write x as some u1 plus u2. Okay, where u1 and u2 are elements from u. If u1, u2 are elements from u, since it is a vector space, u1 plus u2 should be in u, right? So it should be in u. So we started with an element from u plus u and we got that x is in u. So we can say u plus u is contained in u. So we got u contained in u plus u and u plus u contained in u. So u should be equal to u plus u. Fine. Okay. Any other doubt? Any doubt?
No, ma'am. Thank you.
Okay. Yeah, sorry for some trouble. I was having some technical problem from the beginning today. Yeah, sorry for it. Yeah, if you don't have any further doubt, we can stop for today.
Can you share your email ID so that if there is something we can email?
Yeah, yeah, I can. I will type in the chat.
Okay.
Okay, you can mail to this address ma20d503 at iattp.ac.in. Okay. Okay, then let us stop for today. Yeah, we will meet in the next week again.
Thank you.
Yeah, okay. Thank you everyone for attending. Bye.
Bye.